Okay, we're going to be starting with the second part of Chapter 7, Energy, and we're going to be looking at conservation of energy. So we already covered one conservation law, as you recall, the conservation of, um, of momentum. And we also talked about conservation of mass. So this is another big thing. The conservation of energy is like the biggest law. We're going to be looking at that. And we already discussed it a little bit because we talked about how energy can be transferred and transformed. And so that is basically the idea of the law of conservation of energy. The energy doesn't come from nowhere. It has to come from somewhere usually. It can't be created or destroyed, but it may be transformed from one type or another, or it gets transferred from one object to another. But the total amount of energy in the universe is believed to be unchanging. And so often, of course, we apply this to a system instead of the entire universe. So, for instance, we have this girl here who is shooting her bow. And the idea is that she is able to take that energy and it gets transferred and transformed as she shoots the bow. So you can imagine that she is standing there and she is ready to start the day. So she had her breakfast. So what kind of energy does she have? She has chemical and biologically stored energy. Okay, so she's got this energy inside her. Then she raises up the bow, which gives it some potential energy too. And she's holding it so that it's curved and the arrow is notched in the notch there, and the bow is full of tension. So what she's done is taken some of her, that's supposed to be an arm, sorry, some of her kinetic, her biologically stored energy, and she has turned that into spring potential energy. The bow is springy, it's ready to go. Maybe that's her leg. Okay, here's an arm. All right. Anyway, so now it has spring potential energy and a little gravitational potential energy. Then the arrow starts, she releases the bow. The arrow starts to fly through the air. And then what kind of energy does it have then? Well, it's got kinetic energy, right? Energy of motion. Then it plunges into the target. Now, these targets are often straw. They're usually set on some fairly feeble stand so that when the arrow hits them, they vibrate. The arrow pushes its way into the straw, and that creates heat, right? So we start to get heat here. It's getting hot. So heat, of course, is a type of kinetic energy also, the energy of the warm molecules moving faster. That's what's being produced. So we're getting heat. And then we get another type of kinetic energy because the stand is vibrating. It vibrates down into the ground. So you get vibration traveling throughout the environment. So that's kinetic energy, and that would be vibration. And some of that will go into the air. So it'll heat up the air as the stand vibrates. So you get an additional heating of the air, moving the molecules faster. So the energy has gone into the environment now. The world is a little bit warmer because of what she has done. And we do this all the time. You hop in your car and you turn that gasoline into kinetic energy. Then you throw on your brakes, and the friction of the ground causes your tires to heat up as they slow your car, and the brake shoes inside the tire, inside the wheel, are heating up. And so what happens is that you basically turn that gasoline into heat in the end. So we do this all the time. We add this heat to the environment. No, that's not especially what's causing climate change. That is due to trapped heat. This heat would radiate out into space, some of it eventually, except we're trapping too much of it. Okay, now conservation of mechanical energy is the idea that mechanical energy, often what we focus on is just the potential energy and the kinetic energy. So we're not looking too much at the heat and the friction and stuff like that. We're just going to think about usually just gravitational potential energy is what you guys have to worry about, and then energy of motion. And usually we're talking about straight line motion of an object like a car rolling down the road rather than heat energy. And the total mechanical energy of an object or a system remains constant until an outside force changes it. So let's look at something like a pendulum. A pendulum swings and you give it potential energy, and as it swings back and forth, it is changing that gravitational potential energy into kinetic energy. So the pendulum, as it swings, start out here, it's got more potential energy, swings down here in this location, it's going to have kinetic energy, transformed some of the potential energy into kinetic, swings back up to its original height. And this is the sort of thing that Galileo studied. It only goes so high because it only has so much potential energy. So it returns to the same height, the same amount of potential energy that it started with. And so this system of a pendulum, the energy will remain constant. Let's go look at the Newton collider. Remember we looked at that the other day. And so what again the Newton collider is showing is conservation of energy also. So we give some energy to the first ball. The energy gets transferred from one ball to another ball to another ball, finally to the last ball. So it's conservation of momentum and conservation of energy at the same time. Now, eventually what happens is that it stops going because, well, there's the stand is shaking the desk, and so friction and vibration eventually will make it stop moving. And while we're over here, I've got another demo here. This is a little motor. Let me put some more light over here. Let's see if I can pin this. Okay, that's supposed to be looking that way. All right, here we go. What we've got here is a little motor that we have a power supply underneath. Up above is an electrical motor. We'll look at this again when we look at heat, and we'll look at it when we look at motors. So the idea is I'm going to put electricity in and create electrical energy. So electricity in, and I'm going to create kinetic energy, the energy of motion. Right? So this happens all the time. It could be your Tesla, your car, taking electricity and making an electric motor go. You can't smell it, but there's the odor of ozone there. From the, there's a little bit of a spark gap. Okay, now up above, I've got a weight on a spring. So we've got energy transformations here of potential to kinetic too. This is like a pendulum also. And again, it returns to the same height every time as long as the energy lasts. It'll raise itself back up to the same height. But I'm changing it, the spring energy, right? It's the energy is being transferred and transformed. Okay, so some examples of energy transformations. Oh, let's hope my husband gets that. Okay, so let's get back to unpin that. All right. Okay, so for when we're just looking at mechanical energy, a potential energy and a kinetic energy, we can look at something like a ball falling. So here is a ball that we have raised up to 2 meters. And so let's say that we're going to figure out what happens to the energy as the ball falls. So we raised it up to 2 meters. So this height would be 1 meter. This is 2 meters. This is 0 down here. Okay, now the potential energy plus the kinetic energy. When I raise it up, I hold it still. So it's just got 2 meters worth of potential energy, right? And remember, so we just have potential energy. We don't have kinetic because it's not moving. So I would just use the formula mgh for the potential energy. And the mass of this ball is just 1 kilogram. So we're going to have 1 kilogram times 10 times a height of 2 meters. And so we're going to get just 20 there. So 20 joules of energy. Okay, now it goes down lower. Now it's at 1 meter, so it started dropping. As it falls, of course, it's going to start speeding up. So it's going to be gaining kinetic energy. And so now what happens is that the energy, and when it's halfway down, actually it's going to be half potential and half kinetic energy. And we can figure out how much potential energy it has. Again, because we know the height is just 1 meter. So the potential energy is going to be mgh 1 times 10 times 1. So it's 10 joules. Okay, now the idea with conservation of energy is that in this system, the total amount of energy is going to have to be 20. That's how much energy it has up at the top. So that's how much energy we have to play with here. So if it's got 10 joules, which is potential energy, then the other 10 joules must be the kinetic energy. So the total mechanical energy is going to be the potential plus the kinetic, and we know it has to equal 20. So it's going to be 10 plus 10 to equal 20. Okay, 10 joules for both kinds of energy. Okay, now it hits the ground. But when we say something is going to hit the ground, the energy we want to talk about is right before it hits the ground, right as it's kissing the ground. So it's just hitting the ground level. It hasn't begun to stop yet. So it's just in contact with it. And so we would call that our zero potential energy line when it reaches that level. That's where our zero is. And we get to set the zero potential energy line. So we've set it at ground level here, which is usually where you want to set it. But the idea is at the zero potential energy line, there is no potential energy. That bottom of the ball is hitting the floor, so there's no more potential energy. It's zero. And so the thing is, that means that all the energy must be kinetic. And we know it should be 20 because our total still has to be 20. So all the energy has now been transformed into kinetic energy. Okay, let's look at a roller coaster. So the energy of a roller coaster. Now, in your book, and for fun, we often give it labels. So this is an old-fashioned roller coaster. And let's make this top point, point A. And we'll put a point like halfway down. We'll call that point B. And a point down up here, that's C. And let's have another one here. We'll call that D. Here's one at E. And we'll have another one down here, which is F. And both C and F are at the 0 potential energy point. Okay, so anyway, so how does our roller coaster get up there? Well, the roller coaster is going to have to get dragged up there. Something does work. So usually it's a chain underneath that your roller coaster is hooked to. So that's that clink, clink, clink sound you hear as you're going up. There's this chain sort of set up, and it takes you up to the top of the track. And so your roller coaster get dragged up there, and that's a force times a distance, which is doing work. So that work is giving the energy to the roller coaster. So it ends up here at point A with the people in it and ready to roll here. Okay, so at point A, what kind of energy does it have? Well, at that point, remember, you get up there and you're kind of looking around. So most all the energy is just potential, right? You haven't really started the ride yet. So at that point, at point A, the mechanical energy is equal to the potential plus the kinetic, but basically at that point, there is no kinetic. It's just all potential energy. Okay, starts to go down, zooming. So obviously, it's now changing some of that potential energy into kinetic energy. It's lowering the height, which reduces potential energy, and it's speeding up, right? Potential energy becoming kinetic. And so when it reaches point B, which is halfway up, well, then it's going to have, as we talked about before, half of the energy is going to be potential and half is going to be kinetic. So whatever we have up there for potential energy, now we're going to have half of it as potential and half of it is turned into kinetic. Okay, keep going down, zooming down. All right, now your cart is down here at the bottom and it's making the turn. And you feel, a lot of force. Okay, because you're being pushed to go back up. But just as you're reaching that bottom point, what happens to your energy? Well, you're at the 0 potential energy line, so we can't say you have any more potential energy. So all the energy at point C is kinetic. So it's all kinetic. Okay, and then it goes back up. Now, when it goes back up, what happens? You start to regain potential energy, and it starts to slow down. So as you go back up to D, and then to E, and then what happens is that you're regaining some of that potential, that gravitational potential energy. Okay, but you never get as high as you did at A. So when you go over E, you're still moving pretty fast. Okay, because you haven't transformed all the potential energy back into kinetic. But this is also why all the hills that you come across now are going to have to be a little shorter because you need to get over them. And so yeah, until they drag you back up to a great height again, you're just using the potential energy that you got at point A to get over all these lower hills or loop-de-loops or whatever it is they put you through. So anyway, so that's sort of how roller coasters work. Now, one of the things that you're supposed to be doing is comparing the velocities. So you could be ranking this. And you've got some ranking homework problems and test problems. Okay, so let's rank this. We've got the mechanical energy at point A. That's a lot of potential energy. So let's rank it first in terms of potential energy. So if I'm going to rank this in potential energy, the highest potential energy is point A, right? That's where you've got the most potential energy. The second highest point, well, you might say B because that's next in line. But that actually wouldn't be second because E is slightly higher than B, right? And that's the point, is the highest points will have the most potential energy. So the next highest point is actually E. Okay, then you get to B, right? So it's A, then E, then B. What comes next? Well, what's the next highest point? That would actually be D, right? And then what's the next highest point? Well, you've got C and F are actually at the same level. So C equals F, okay? Those two have the same amount of potential energy, which is 0, because they're on the potential energy line. Now, what about kinetic energy? Well, kinetic energy should be the opposite. So even though at point B you're screaming a lot, the place where you're actually going the fastest is point C. C is where you are going to have turned all that potential energy into kinetic energy. And F also, okay, if it's a frictionless track, then your speed at C and your speed at F would be the same. If there was friction, then F would be a little slower. Okay, but when we do kinetic energy, basically we do the opposite of potential. So we would have C and F are the fastest. And so then we would go backwards, D, B, E, and A. A would be the slowest, right? In fact, there's no speed at A. Okay, so now we've ranked them. Potential energy and kinetic energy will be opposites of each other. Okay, now there is something though. If you've ever ridden Raging Bull at Six Flags or Magic Mountain or wherever it is, anyway, it has a section where you go under the ground. Okay, so that changes things a little bit. So when you go under the ground, so let's make point F our underground point now. Okay, now definitely F has the lowest potential energy. In fact, it would be negative potential energy because it is below the 0 line. So yes, we can have negative potential energy. Like the center of the earth. We usually measure things to the ground. But what if you dig a hole in the ground? That's below it. So that's okay. It doesn't mean bad. It just means kind of other direction as usual. And so F would definitely be the all by itself the lowest. But what about in terms of kinetic energy? Well, F would also be the fastest point. So next time you ride Raging Bull and you go into that dark section under the parking lot, what's happening there is that you are actually going the fastest too. So very exciting. And if you ever get to go to Mount Olympus Water Park and ride a ride called Hades, they have a section underground too. But instead of being a safe roller coaster, that is an extremely rough roller coaster with very few straps, very painful actually to ride. So anyway, so yeah, so I did it once, but I'll never do it again. Okay, so let's look at some numbers here. So let's have our roller coaster. Okay, and let's say that we want to figure out what the potential is at A. Well, we can easily do that. And let's make this 40 meters high. Okay, And our zero potential energy line is here. So here we've got A, let's throw in B, and let's throw in C. Okay, so let's figure out the potential energy at A. Pretty easy, right? Potential energy at point A would just be mgh. And the h will be the height above that zero line. Okay, so this is your zero potential energy line. And let's make the mass of the car 1,000 kilograms, because that would be about what it probably would be. So 1,000 kilograms. Then you would multiply by 10 meters per second squared, and then you would multiply by the height of 40 meters. And so you would end up with 400,000 joules of energy. That's a lot of energy. Okay, now down at the bottom, at point C, that's going to all get turned into kinetic energy. So the kinetic energy will equal 400,000 joules at point C. So the potential energy at A becomes the kinetic energy at point C. Okay, so let's figure out how fast this is going then. So we're going to make this, which is our potential energy, it's also going to be equal to our kinetic energy at point C. And remember, the formula for kinetic energy is 1/2 mv squared. Okay, so let's solve this for the velocity. So we'd have 400,000 equals 1/2 m, and the mass is 1,000, v squared, and that's what we're looking for, so we're going to leave that alone. Okay, so we've got 400,000 equals 1/2 of 1,000, which is 500. So we're going to cancel 1,000 on both sides. That's easy. Multiply both sides by 2, and we're going to get 800 equals v squared. Okay, so I multiply both sides by 2 to get 800. So now I just have to take the square root of both sides to figure out what v is. So what's the square root of 800? Yeah, that's what calculators are good at. But you might think to yourself, well, let's see, if it was 10 squared, that would be 100. If it was 20 squared, that would be 400. If it's 30 squared, that would be 900. So it's probably kind of close to 30. So let's say it's 26 or so. Let's see what happens. All right, well, let me see if I can get the proper answer here instead of just guesstimating. Oh, 28.3. Okay, so 28.3 meters per second is equal to the velocity. Okay, so now we know how fast it's going at point C. And that should be the maximum speed this roller coaster reaches, unless it goes underground. Then it will go faster. And you would have to think 40 meters plus, if it went 5 meters down, you'd have to add that. So it'd be like 45 that it dropped. Okay, so anyway, so we figured out how to get the velocity of the object. Okay, now what about at point B? Does that mean at point B it's going half that speed? No. Energy, if you double the speed, that's 4 times as much energy. Well, we don't have 4 times as much energy here. So at point B, it's actually going to be going much slower. Okay, it hasn't transformed enough energy yet to be even half the velocity. Okay, now is there an easier way of doing that? Yes, there is. You can think about what we did. Let's go back to the slide for a minute. We multiplied by the mass here. And then down here, we had the mass again, so we divided by it. Well, that seems a waste of time. And so, yep, sure enough, that is a waste of time. The idea is that the potential energy at the top, or the potential energy, will get converted into kinetic energy. And both of those terms have mass in them. So we can cancel the mass and just do the other parts of the equation. So down here shows what happens. So here's the equation. Now this delta is delta H. That's the height that it drops. Okay, so because that's the energy, the potential energy that gets turned into kinetic energy, because that's what you're saying here. Here's how much energy was changed, the potential energy change, and it got turned into kinetic energy over here. Okay, so delta H is the height that it drops. And so now we've gotten rid of the M in this second one. Now we move the 2 over. So we get V squared is 2g delta H. And now we solve for the velocity, and we get this beautiful formula. V is equal to the square root of 2g delta H. Okay, so let's say we took the numbers we had earlier. The roller coaster was 40 meters in height. So it's going all the way down to 0. So that's a change of 40 meters. So if we just plug that in here, we would get square root of 2 times 10 times 40. And that is square root of 800, which we already talked about is 28.28. So this works, right? And not only that, but you can now find the speed at any point along here. So if I want to find the speed at B, let me put in a new slide. So let's say I want to find the speed at B. So point A was at 40. And point B is 20 meters high because it was half as high. Okay, so let's say I want to find the speed at B. Well, I would just use that formula. Velocity is equal to the square root of 2g delta H. Oops, let's be an H. And so the velocity would be equal to the square root of 2 times 10. And the change in the height is it's dropping from 40 down to 20. So that's delta H. Delta H is 20. That's how far it dropped. So it's not where it ends up. I mean, it is actually at 20, which is probably a mistake to use. But the idea is how far did it drop? Just like if you're using this for point C, your drop height is 40 because it dropped 40. Okay, so we're going to use 20 in here. And so now we've got the square root of 400, which actually is 20 meters per second. So we got a lot of 20s running around there. But anyway, the idea is that, yeah, you can calculate the velocity at any point along the track just by figuring out how far it dropped. And so if I want to go to point D, which was around here, let's say that was 5 meters high, then that means its drop would have been 35 meters, right? So from A down to point D, 35 meters. And so anywhere along the track, I could figure out what the velocity is. So this is a great formula. Now, this formula is also for any object that's falling. Because this was a frictionless track, we came up with this formula. But that means that it also works for any falling object, because you're just saying potential energy goes to kinetic energy. And you don't specify how it got there. So it could be on a track, or it could just be falling. And so this formula is in your equation sheet under falling objects, okay? So it's very handy when you only know the height, you can figure out the velocity. Or you could turn it around. I could say I'm throwing a ball up in the air and I've given it an initial velocity of 5 meters per second. How high will it go? Well, now you can do that. You could say, okay, I'm going to figure out the height because I know the velocity. So you could turn it around. So you can use this equation in your homework where you're being asked about how high something will go too. Okay, so that's the end of that for the moment. And we're going to go to part 3. So we're stopping conservation of energy.